In the Anatomy and Physiology 2 chapter on blood vessels, the beginning is about one central theme, the different kinds of blood vessels and how blood flows through the body. The end of the chapter is kind of naming all of the blood vessels as one goes to, say, the brain and back, etc. The middle portion of the chapter has a lot of little topics. And so if this video, which is kind of an overview of this middle part of that chapter, if it seems a little disjointed, my apologies. It's because of that reason. And so if you had any desire to go into any of these topics in greater detail, the videos that I'm kind of summarizing, obviously they do go through it to more detail. So one topic is how does transport happen across capillary walls? Well, oxygen gas is I'm sorry, before I apologize, that work extremely. There are spaces, even continuous capillaries can have intracellular clefts, which would allow material to leave. But blood can't leave because blood cells are too big to fit through those spaces. And then even these proteins are too big. And so blood does not leave capillaries. Blood cells and blood proteins are simply too big to fit through those spaces. There are nonpolar gases which can be in blood, such as oxygen and carbon dioxide. And since they're nonpolar, then they can actually pass through cell membrane space. So I can have carbon dioxide going up. There are ways that transport can be managed. Water can fit through these holes. Then anything that can dissolve in water, which is polar, can then go from an area of high concentration to low. So sugars, amino acids, even urea can go from an area of high concentration to low. And you may remember from Anatomy and Physiology 1 that there is a process known as phagocytosis, where cells can eat a solid object. They extend these little extensions from themselves, they engulf an object, they form a vesicle, and this then comes inside. Well, cells can do that with liquid as well. So just as phagocytosis is compared to cell eating, then penocytosis can be compared to cell drinking. So those endothelial cells can engulf fluid, say from the plasma, form a vesicle, and then transport that vesicle across the width of the cell, and then expel it outside the cell. That's known as vesicular transport. And so there are a number of ways that materials can be transported across capillaries. However, the major way is the final thing that I will describe. The major way involves pressure and is therefore called bulk flow. So if you were to ask what's the major reason that substances are being transported across this capillary wall, the reason is because the heart squeezed the blood very hard, and now there's a pressure, a blood pressure that we could abbreviate BP, although you could also call it blood hydrostatic pressure and abbreviate it BHP. And so because of the heart squeezed very hard, there is now blood pressure, blood hydrostatic pressure in this blood. And now we have a tube that has holes in it. So just like if your garden hose had holes in it, when you turned on the water, water would come out the holes, going from an area of high pressure to low. The same thing will occur here, that we will see blood pressure will tend to push fluid out of this capillary, and then other substances will go with it. All right, and so bulk flow means that it is pressure which is pushing fluid through these spaces, and then anything that's small enough to fit through these spaces as well, not the blood cells or proteins, but these smaller molecules, then they can then be transported as well. Now, if we were to talk about this, it is a tiny bit more complicated because there is typically fluid around these blood vessels. There's a tissue fluid, an interstitial fluid, and then it then has pressure. Not only does it have pressure, but water will tend to go to where the solutes is through osmosis. So osmosis is water tends to go to where the solute is most concentrated. And when you look at these blood proteins, since they can't leave the capillary, then the blood capillary is where the solute is most concentrated. So osmosis would tend to draw water into the capillary. So there's actually two separate pressures, a blood hydrostatic pressure pushing out, and then an osmotic pressure pushing in. So the blood pressure, all right, because the heart squeezed very hard, would tend to push water out. That's an outward flow. And then the osmotic pressure is where osmosis will tend to draw water to where the solute is. That's an inward flow. And so there are these two pressures, and it's a pushing match. But at this spot of the capillary, where the capillary begins, at the arteriole, here the blood pressure would average maybe 35 millimeters of mercury, while the osmotic pressure may be 25 millimeters of mercury. And if you notice, the bubbles are going outwards. There is a net outward pushing, pressure. The net filtration pressure goes outwards because the outward pushing blood hydrostatic pressure exceeds the osmotic pressure. So there is this net outward force. So that's great. However, that's then a problem because you've lost fluid out of your blood, and by the end of the day, you will need it back. So that fluid which just left, it has to come back. And it does at the other end of the capillaries, the venule end. At the venule end, you might notice that the bubbles are flowing inward. At the venule end of the capillary, the osmotic pressure is still 25 millimeters of mercury, but the blood pressure has reduced because now there is less fluid in the blood, and now the blood pressure is 17 millimeters of mercury. Once again, it's a pushing match, but now the inward pushing osmotic pressure wins, and so there is a net inward force at the venule end. And so the major form of transport across the capillary is what's called bulk flow. It is pressure which is primarily pushing water through spaces between capillary cells. And because of this, anything which is small enough to fit through those spaces will go with the water. So let me just kind of repeat that. If this is the arterial end where the capillary is starting, here's the venule end where the capillary is ending. Notice here the bubbles are going inward, and there the bubbles are going outward. Why? Well, because the osmotic pressure is the same all throughout, the tendency of water to go to where the solutes are. There are proteins which the liver has put in the blood on purpose. So the liver wants there to be more solute inside the blood than in the tissue fluid. So therefore there is an osmotic pressure drawing fluid in. But here at the arterial end of the capillary, where the capillary begins, the blood pressure is still high. And so the net outward pushing force is greater than the inward pushing force. And so at the arterial end, the BHP is greater than the BCOP, and fluid will leave the capillary. That's great, but we need that fluid back. And so then when we go to the opposite end of the capillary, the venule end of the capillary, here, the osmotic pressure, which is 25 millimeters of mercury, is greater than the outward pushing blood hydrostatic pressure. So here the bubbles are going back into the capillary, showing that there is a net inward force. So that's how the major form of transport at capillaries. But this is very important, especially for those who go into healthcare. Because things like dehydration, inflammation, these are very important. And we notice when fluid is in capillaries, the way. And so if disruption, where now the was great, we would notice changes in fluid was in fluid accumulating out a number of reasons, blood, and a number of other causes such as venous valves, so edema, blood or fluid, they account for a number of reasons. Based on highly like things which we had the liver makes these water into the capillary. The other one is malnourished. The liver isn't making as many fluid leaves, is less likely to have seen a photo of a starving child with it. That is because the nourished child making the plasma proteins which water back in. This tissue was dying and bursting by bacterial toxins. First, the is outside the tissue outside the blood vessel. There would tend to be fluid entering into the capillary there, and so it would tend to swell because the blood pressure would be less. Now there would be more the capillary. This transport is certainly very important. Fluid accumulation, obviously, very as well. I used the term vasoconstriction before, and I'm about to do it a few more times. So let me just kind of talk about that one last time. We have muscle in the lining of blood vessel walls. It's still capable of constrict. The lumen gets on pressure increased. Vasodilation. But remember to I've spoken of blood clotting. That when we cut ourselves, platelets can release factors which cause a vascular spasm, so that the muscles will then constrict and cause vasoconstriction. And so there can both be neural commands sent here, and then also locally acting hormonal factors can also cause vasoconstriction. Not only does this affect blood pressure, but it will also then help direct blood flow, as we will see, because you have 5 liters of blood and 8 liters of space. You just don't have enough blood to go everywhere. And so you would tend to send blood towards your muscle exercising, but in the rest you would send blood more to your small intestine for your immune system. And so vasoconstriction is for that. Now, on the topic of blood pressure, one could ask a preliminary question: how much pressure do we need? And the answer is, well, the resistance of blood flow doesn't move for free. You can't say, hey, just go to the hand and back. It does go. There is resistance to blood flow. And so therefore, the blood pressure that you need to generate is sufficient to overcome the resistance to blood flow. So you need to understand the sources of resistance. There are major determinants of the resistance to blood flow. First is blood viscosity. Second is blood vessel length. And third is blood vessel diameter. And so you need to understand these before you can, determine how much blood pressure do I need to generate in my body to circulate blood throughout. So if you've ever had the experience of, you get a drink like maybe water or an iced tea and you try to drink it through a straw, that's rather easy. If you now do that with a milkshake, it's much harder. It's harder to move a thick fluid than it is a less viscous fluid. So the greater the viscosity, the thicker the blood, the harder it is to pump. Now, blood is thick, right? So we start with water, and then we add plasma proteins to it that increases the viscosity from 1, which is the viscosity of water, to 1.5. But then we add red blood cells, white blood cells, and platelets, primarily red blood cells. And now the blood is much thicker, and it has a viscosity of 5. Blood is 5 times thicker than water, and this makes it harder to pump. And we know that some individuals have thicker blood than others, all right? And so if you're male, then your blood is going to be thicker. Your hematocrit is greater. In women, it tends to be less. So male blood tends to be thicker. Male blood is harder to pump. Men need higher blood pressures than women, all other variables being equal, which is one reason that while heart disease can affect both men and women, it tends to affect men earlier in life because they have higher blood pressure throughout their lives than other conditions which would elevate or make blood thicker, such as the use of erythropoietin or blood doping. Or if, let's say, you lived at a higher altitude, you get the same thing. So you would have more erythropoietin released at a higher altitude. This would tend to thicken your blood, and other conditions like being anemic would tend to make your blood less viscous. So there are variations in blood pressure from person to person, in part because there's variations in how thick your blood is. The greater the thickness of blood, the harder it is to pump. Now, once I had an AMP2 class, and there were these 2 students, and I know it's in part inappropriate to, dwell on something revolving around, their physical attributes. But this was such a distinctive case that I think, it's a good teaching moment. So this one lab table had this very petite a woman, and then her lab partner was this gentleman. Now, my recollection is that she stood 3'2" and he stood 12'9". I'm probably exaggerating, but not by much. I mean, if you walked into the room, you would be struck that these lab partners was, a very small woman and a very large man. And when we were doing the blood pressure lab, they turned to me and they asked, so what blood pressure are we shooting, for? So what's normal, 120/80? And it was just this wonderful teaching moment, because the answer is no. And, just look at your lab partner. Do you think your hearts are doing the same amount of work? Do you think that it is just as easy to pump blood through your lab partner's body as it is yours? Because remember the blood vessels, right? We have so many blood vessels that on average, we have 60,000 miles of vessels in our body. Now, many are microscopic, but nevertheless, they're there. But that's the average. The bigger you are, the more blood vessels you have. And obviously we can be big in a couple of different ways. We can be taller, we can have broader shoulders. And so thus the bigger we are in that sense, the more of these blood vessels that we have. But then obviously we can be large in other ways as well. We can gain adipose. Now, adipose has blood vessels in it. Every pound of adipose has about 180 miles of blood vessels. So let me just repeat that. Every pound of adipose that we gain in our bodies has about 180 miles of blood vessel. Now, most of these blood vessels are microscopic. But then the fact is, let's say we gain 10 pounds. Let's say we gain 20 pounds. Let's say we are 50 pounds overweight or more. We are not just gaining weight and adipose, we are gaining blood vessels, miles and miles and miles of them. And now your heart has to work. So the signal, which then helps with blood pressure you need, blood vessel like water pipes, and that's you need in the water. In a house, you need less if it's going to an apartment. Longer pipes of the apartment require greater pressure. So the same is true in humans, just as you need more pressure to push water through more piping. You need more blood pressure to pump blood through more blood vessels. So the larger we are, whether that be height, the width of our shoulders, or the adipose we gain, the more blood vessels we have, and thus the higher the blood pressure that we need. Finally, the third variable is the diameter of the blood vessel. And so just a quick analogy. If you're in your garden and you're trying to water your garden and you're at the edge of your water hose and you don't quite have the ability to spray water on that last flower bed you wanted. Well, you all know that you can take your thumb, you can put it over the opening of the garden hose, and now the water shoots further. And that's because if you take an opening that looks like this, and then you squeeze it and make it look like this, as the diameter of the opening gets smaller, the pressure goes up. And that's the higher pressure that you then use to squirt that last flower bed. All right. Well, we can squeeze blood vessels and make them narrower. We can do vasoconstriction. We can also do vasodilation. All right. And so therefore, the narrower we make this tube, the higher the pressure you'll need to push, blood through it. Now, a number of things can do more vasoconstriction than normal. So for example, if you're under stress you release epinephrine, and that will then cause vasoconstriction. If you're a smoker, all right, nicotine can cause vasoconstriction. So these are things that we can do which will raise blood pressure. When we smoke, when we're under chronic stress, our blood pressure also rises. If we're developing lipid plaques because of heart disease, that's narrowing the lumen of the capillary, and thus now the amount of blood pressure you need to push blood through this opening increases. So how much blood pressure do you need in your body? Well, you need enough to overcome the resistance to blood flow. Blood doesn't move for free, so you need to push it hard enough to get it to your brain and back, your hand and back, your foot and back. What determines this resistance? Three things. How thick your blood is, the thicker your blood, the harder it is to pump. How long are your blood vessels? The longer your blood vessels, because of the size of your body, the harder you need to pump. And then finally, the narrower the diameter of your blood vessels, the harder it is to pump fluid through them, the more blood pressure you need. Okay. Now, this next question, obviously, we can change our blood pressure from moment to moment, and we can always make it sufficient to what our body's needs are. And we can also direct blood flow, right? As I said, you have 5 liters of blood, 8 liters of space. Right now, you're choosing where in your body you would like blood to go. So how do we do this? Well, 3 ways. And actually, I asked 2 different questions. The 3 ways are the same answers to both of those questions. So how do we regulate our blood pressure? How do we determine what it should be and make it go up or down as we see fit? Well, there are 3 ways. How do we decide in an emergency to send more blood to our muscles, and at rest to send more blood to our digestive and urinary systems? The same 3 ways. And so then what I'd like to do is to answer these 2 questions together by going through the 3 ways that we regulate our blood pressure and the 3 ways which we guide our blood flow. So first of all, there are neural reflexes, all right? And so neural reflexes help us determine this. Now, in a reflex, think of the patellar reflex when your reflex are tested with a doctor. The doctor hits you in the knee, you feel that stretch, all right? And then the reflex involves muscle contraction, right? So you straighten your leg. So there was stretch, it was detected, and then we have a muscle contracting as a response. Well, you have stretch receptors in your blood vessels. You know to what degree your blood vessels are being stretched. We have stretch receptors in the aorta, right where the common carotid divides to make the internal carotid and the external carotid. There's an area where there are receptors for pressure. Actually, if you ever dissect a frog, you may even notice that there's a little bulb here, right where the common carotid divides to those 2. There's actually a bulb called the carotid body, which houses these receptors. So your nervous system is aware of what your blood pressure is, how much your blood vessels are being stretched. You are measuring this. So these receptors then tell the brain, the medulla has a cardiovascular center. And then the medulla can then send commands to muscle. Remember that nerves can go to the muscle in the tunica media and cause vasoconstriction. And so your brain is aware of what the pressure is in blood vessel walls and how much you're being stretched. And then your brain can send commands to then cause more vasoconstriction or then to cause less, and thus do vasodilation. And so thus we can control our blood pressure, all right? And then, if vasoconstriction happens over here and vasodilation happens over there, we can also then help direct blood flow. Blood will tend to go into the blood vessel where there's vasodilation, less blood into the blood vessel where there's vasoconstriction, all right? So neural reflexes are in part an answer to the questions. Okay. But then hormones can also cause vasoconstriction and vasodilation. So thus hormones can help direct blood flow and what your blood pressure is. Now, some of these hormones act from far away, so that's where I'd like to start. So in the kidneys, there are these JG cells, all right, of the glomerulus, also known as granular cells, that make the hormone renin, all right. Renin then activates a liver protein. The liver protein is known as angiotensinogen, and renin converts it into angiotensin, all right. So angiotensin is now a signal which goes in the blood this blood then reaches the lungs. The cells of the lungs then make an enzyme called ACE, the angiotensin converting enzyme, which converts angiotensin 1 into 2. Just a quick note, this enzyme is the a receptor for the coronavirus to enter human cells in the lungs. That's a separate discussion, but when you hear of, the ACE protein, that's significant then in that sense. Okay, so long story short, there is this hormone in the blood now called angiotensin 2, which is released when your kidneys have realized, hey, we're not making as much urine. I think that's either because A, we're dehydrated, or B, we're lacking, blood volume, maybe because we were bleeding. We need to fix that. And so angiotensin tells your body, we now need more blood pressure. So this system, the renin-angiotensin system, this is the major hormones which regulate blood pressure in addition to other things, and are thus very important. All right, so that's a major hormone system regulating blood pressure. Now, those aren't the only hormones which are involved, the renin and angiotensin system, and thus we could get into other aspects which affect, blood pressure. Now, I just want to mention this because it becomes very important later, but the amount of fluid in your blood obviously then determines its pressure. All right, so the more fluid you have in the blood, the greater the volume, the greater your blood pressure. And so there's this balance that we hope to strike. You have fluid in your blood plasma, you have fluid in your potential urine, the filtrate that's becoming urine. And there are times where you're dehydrated and you're trying to move fluid this way. So you make less urine and you keep more fluid in your blood. And then there's times where you are trying to secrete more fluid. And so renin causes the production of ADH, which causes us to reabsorb water, and then aldosterone, which causes us to reabsorb salt, which helps us reabsorb more water. In any case, these hormones help fluid go this way, increasing blood volume and pressure. Whereas the heart sometimes realizes, wait a minute, I think you've been drinking water all day, because now there's too much water, there's too much blood volume, and I have to pump this. I'm not fond of that. And so then the heart can make a hormone called ANP, which causes now to move more from blood plasma and treat it in. So those are more hormones. Obviously, during an emergency, hormones that we release is epinephrine and what's also known as adrenaline and noradrenaline. And then, so while there's vasoconstriction all over the body, which then increases blood pressure, more blood will end up going to muscle and less to the digestive system, et cetera. And so vasoconstriction, which we see in the body, can then be to varying degrees, and it can help to direct blood flow. So doing a bit more dilation on the blood vessels going to muscles will cause more blood to go to muscles, more vasoconstriction going to digestive and the digestive system, the urinary system, the reproductive system, the immune system, means that these systems would then get less. And so that then indicated that in addition to the nervous system having a control, a say on what your blood pressure is and where blood is going, so do hormones acting from afar. Now, some hormones and chemical signals are very locally acting. So tissues can actually regulate themselves by making locally acting factors rather than waiting for, renin coming from the kidneys or angiotensin 2 coming from the lungs or epinephrine coming from the adrenal medulla. And so when a tissue regulates itself, we can refer to that as autoregulation. And so there are a number of ways that tissue can regulate itself. First, the smooth muscle of the tunica media can regulate itself just a little bit on its own. There's what's known as a myogenic mechanism. If it's being stretched too much with dilation, it can then constrict on its own, all right? If it's not getting enough pressure, it can then dilate on its own. So this is then the myogenic mechanism where the smooth muscle will act by itself then to either do vasoconstriction or vasodilation, and this then has effects on blood pressure and where blood goes. There are additional factors which can cause vasodilation. And so if you ask, why is this blood vessel dilating, it's not because of the nervous system or hormones coming from far away, but rather nitric oxide released locally or adenosine released locally. Or this could just be a result to low oxygen levels, carbon dioxide levels, high acid. The tissue knows you've been exercising this tissue, it needs more blood flow. And so it then causes vasodilation, bringing more blood to that area. Inflammatory signals, histamine, all right, can now direct more blood to, say, a tissue which is injured. So if you injure a part of your body, it might get swollen and red because the inflammatory signals in histamine are bringing more blood there for white blood cells, for repair, because they're causing vasodilation. So these are locally acting factors which can cause vasodilation through autoregulation. And then there are also locally acting factors which cause vasoconstriction, such as endothelins and the vascular spasm that would occur during clotting. So if platelets realize we've been cut in a place, they release things which then cause a vascular spasm. Less blood will be delivered to the region which was cut. And so if you were to ask, how then do I regulate my blood pressure to meet my body's needs? How do I decide, should more blood go this way to muscle or more blood this way to the small intestine? And the answer is we have neural reflexes which have a role in this. There are hormones, which can travel, distances throughout the body, which can affect this. But then there can also be autoregulation as tissues make factors which cause vasodilation and vasoconstriction. So these three ways, neural reflexes, hormones, and autoregulation, are both how we regulate our blood pressure and how we direct where blood goes in our bodies. So when I teach this course, the first part was arteries versus veins and how blood goes through the body. The middle part of the blood vessel chapter then has a number of diverse topics which I've just gone through. The final part of the topic is more naming. So here's the brachiocephalic trunk, here's the common carotid artery, here's the internal carotid artery, et cetera, here's the subclavian artery, and to get blood flow to the brain and back, you would go this way or that way. In our coursework, that's more of a lab topic, and so the overview that I give this playlist has a lot more videos that are more, how would you get blood to the brain and back? How would you get blood to the hand and back, in what order? But like I said, because that's more of a lab topic, this video will end, and then it will be more of a lab video, which then considers the order of the blood vessels after they've been named.